Okay, so now we will start the lecture. Myself, Hari Shankar. I am a scientist in Disaster Management Studies Department of IARS, Dehradun. So today's topic is time series interferometric SAR, and particularly we will discuss the PS InSAR. PS InSAR means persistent scatterer interferometric SAR, and SWAS. SWAS is a small baseline subset analysis. So these are two advanced techniques of the SAR interferometry for time series analysis. Time series analysis of deformations. Deformations means if any types of the deformation has occurred on the Earth surface, deformation may be in the form of land subsidence or landslide, or it may be like a glacier melting or deformation. Just a minute. No? हेलो हाँ स्टार्ट कर दिया हाँ हाँ कर देते so the deformation may be land subsidence or landslide or glacier melting or deformation due to the earthquake, because when the earthquake happens, so there may be a lot of damage of the properties or the land, so that is also called the deformation. And volcanic eruption or any other infrastructure deformation, like some buildings are tilting or some bridges are tilting or dams are moving from one location to another location. So all such activities are basically called the land deformation problems. So all these deformations can be monitored with the help of interferometric SAR techniques over a period of time. Over a period of time means time series analysis. So here we will target two advanced technique of SAR interferometry, that is PS InSAR. In short, we also call it PSI, and the SWAS technique. Okay. So yeah. So if you talk about the introduction to the land deformation, so there are a lot of anthropogenic activities on the earth surface, like landscaping is there, tunneling is there, mining is also there on the earth surface, water extraction is there, or some natural pumping is there, or coal or like the petroleum products are extracted from the underground. So because of this, certain deformations are occurring on the earth surface, and those deformation or those anthropogenic activities basically changes the geometrical properties of the earth surface, and those geometrical changes may be in the form of the translation and the deformation. Translation is just like a displacement of the target on the earth surface from one place to another place. So the translation may be in the form of the displacement, and that displacement may be in the horizontal directions like the east-west direction or north-south direction, or it may be in the vertical direction also, like the upward movement and the downward movement. So if the movement is downward, so it means the land surface is going downward, which is basically called the land subsidence. If it is going upward, then it is called the land upliftment. Okay. And if can you please mute your mic because some noise is coming. Okay. So that displacement or the movement may be in the horizontal direction also. If, well, for example, if landslide is occurring in a particular east-west direction or southward direction, or north direction, or in a inclined direction also. Okay. So whatever the movement of the target on the earth surface is there, that movement can be depicted with the help of the SAR interferometry very easily. So land deformation may be like earthquake deformation, volcanic eruptions, and infrastructure deformation like dam tilting, bridge damages, building damages, etc. And others may be like faults and the cracks, plate tectonics, because of tectonic plates are also moving over a period of time, but the motion is very slow. So that slow motion can also be monitored with the help of the SAR interferometry and the glacier meltings. Okay, so these geometrical changes had happened on the Earth's surface because of two regions and or two causes. So first cause is the geological cause, and another one is called the man-made cause. So geological cause may be the carbonate dissolution, where the calcium carbonate is dissolved into water, and calcium and the carbonate ions are separated. So because of that, some deformation has occurred, and natural sediment compaction processes are also there. Dewatering is there, drainage or the organic soils is there, earthquake, liquefaction, crustal deformation, sediment loading, tectonics, and biochemical processes. These are all geological processes by which the geometrical changes on the Earth's surface has occurred. Okay. On the other side, there are man-made causes also, like extraction of the natural resources through mining, like the coal, ores, or salt, etc. Because all such ores or the coal is extracted from the subsurface, so subsurface material is extracted, it means the upper surface of the surface is going downward. So because of this downward movement, some deformation has occurred and some displacement has occurred, and this displacement you can also monitor with the help of the SAR interferometry technique. Similarly, over fluid pumping, like groundwater extraction for the agriculture purpose or some drinking purpose, like in metropolitan cities, a lot of groundwater is extracted, and because of that, subsurface the water level is going down, and the aquifer systems are compacting, and the upper surface is going downward. So you might be aware, worldwide there are many cities which are subsiding slowly just because of the overflow pumping problem. Similarly, petroleum products are also extracted from the subsurface or from the underground of the earth surface, and the natural gases are also extracted. So because some material is extracted from the subsurface level, so the upper surface is moving downwards. So this causes, or this reflected into different types of the deformations. Similarly, overloading effect is also there, because nowadays high-rise buildings are constructed, especially in the metropolitan cities or the industrial areas, where a lot of loading effect is there, and because of that, the land is subsiding slowly downwards. Okay. Similarly, the encroachment of water bodies is also there, because earlier some ponds or lakes were there. Now, due to the encroachment, they are putting some, soft material, and over which they are constructing different types of the buildings and so on. And those since the subsurface level is not that much stable, and when you are putting some load over that, so that land is going downwards. So that is also called one of the problem of the deformation. Okay. So all such information, the causes basically changing the geometrical properties of the Earth surface. Because of that, some translation is happening or some deformation is happening. So and those deformation in the translation can be monitored with the help of the SAR interferometry. Now, the importance and the impacts of the surface movement, or you can say the translation and the deformation. So this information, especially the surface movement information, can be used for number of applications. So it has a lot of importance. For example, if you see here, the infrastructure design and construction, because if you don't know the surface movement information, means the stability of the ground surface, then you cannot plan the infrastructure design and construction in the urban areas or in any other areas, because you cannot proper design the infrastructure. For example, if you want to construct the national highways, so you cannot construct those national highways on the unstable lands, means the land which is not stable, and the land is going downwards with respect to time. So over that, the national highway construction is not suitable. So if you see, if you don't have the surface movement information over a period of time, then you are not able to plan the infrastructure design and subsequent construction over that place. So this it means the surface movement information affects the infrastructure design and construction also. Similarly, sewerage and drainage system design, especially in the urban areas, because every city has the sewerage systems, water pipelines, and the other gas pipelines also. So if you don't have the surface movement information, then you cannot plan this infrastructure or sewerage or pipeline network in the cities properly, because somewhere if you are putting some pipes and after some times the movement had happened and those pipelines and the sewerage network will broken. So if it is broken, it means there is a loss of property also. So ultimately this planning or the sewage system planning is somehow related with the surface movement information also. Similarly, subsurface utility planning is also affected by the subsurface or surface movement information. So you can say a surface movement information has a lot of importance in subsurface utility planning. Similarly, seawater intrusion control, flood mitigation inland and the coastal. Because if you see the flood mitigation, it means a general notion is there, like every year the sea level is rising. Hmm? Sea level is rising, it means this is the impact of the climate change, because temperature is increasing and the glaciers are melting, water is going into the sea. That's why sea level is rising, and because of that the irregular rainfall is there. Because of that some flood problems is also there in the inlands. But nobody is thinking whether this phenomena is correct or not, because in reality the sea level surface is rising, or the inland flood problems are occurring. What is the main cause? So the land subsidence may be one of the cause, because it is not necessary always the excess of flood is there, excess of rainfall is there, because of some flooding problems are occurring. But there may be problem like land is subsiding, and because of that the water is not able to flow properly. That's why some water logging problem is occurring at that particular place, and because of that every year some flood is coming. So you can say the flood mitigation or inland or coastal flooding may be because of land subsidence also. Land subsidence means land surface information. So you can, my point here is there may be one cause of flood, like the land subsidence. Because of land subsidence also flood problems are occurring. Similarly, the groundwater extraction, because especially if you think in the India, so there is India is agricultural major crops are there in the India. So for agriculture purpose, lot of irrigation is required. That's what we are extracting lot of groundwater. So if you are extracting a lot of groundwater, it means water level is going down and there is a shortage of the water. And we are not able to plan the which crops should be grown, and in which pattern we have to seed the crops. Okay, so proper planning or the groundwater extraction regulation. That's why we have a groundwater or the water resource ministry. So they are responsible for proper management of the water resources in the country, whether it is underground or the surface water. So accordingly, they are putting some regulations, and those regulations are somehow related with the surface movement information, like this land subsidence or upliftment or some other factors which are related to the surface movement. So all these things are basically affected by the surface movement information, and hence it has a lot of impact on the, because surface movement information affects the buildings, facilities, and the infrastructure. It means infrastructure impacts it has. Some buildings are cracking or tilting, sinking, or breaking the pipelines, malfunctioning of the sewage system in the cities. It means some infrastructure impact is related with the surface movement information. Similarly, land surface, river, canal, drainage flow systems are affected if surface movement is not good, or adverse situations are there. That's why the land surface or the inland coastal flooding, inundation problems occurs, which means environmental impact also related with the surface movement information. Similarly, the infrastructure impact is there, infrastructure damage is there. It means infrastructure is somehow related with the money, or the economic impacts are also there. Because if infrastructure is impacted, it means increase in maintenance cost, decrease in property values, disruption in the economy. It means economic impacts are also there. And if economy is impacted, environment is impacted, infrastructure is impacted, it means the human resources, or you can say the society at a large, will also get impacted from these types of the information. So we can say the surface movement information is directly or indirectly impacts the infrastructure, economy, environment, and the society at a large scale. Okay, so it is very important to monitor where surface movements are occurring in the form of the displacement or in the form of the deformation, so that we can rescue, or we can reduce the impact on the infrastructure, economy, society, and the environment. Okay, so if you see this slide, then you will realize what are the importance of the surface movement, as well as its impacts on different types of the domains. Now coming to the microwave remote sensing, because this technology will help us to monitor those surface movement information, or you can say the deformation, or the translation, or the display. All are interchangeable terms which I am basically using here. Okay, so all such things we can monitor easily with the help of the microwave remote sensing, particularly the synthetic aperture radar remote sensing. In short, we call it the SAR remote sensing. Okay, so you might be aware, because microwave remote sensing may be passive or the active. Passive means radiometers, active means imaging or non-imaging, RAR, real aperture radar, synthetic aperture radar. So our lecture is focused on this SAR, that may be the InSAR or the DINSAR, interferometric SAR and differential interferometric SAR. Non-imaging may be altimeter or the scatterometers. Okay. So this graph is also, you are also aware about this graph, because different wavelengths are there. So one range of wavelength is there from 1 mm to 1 meter. That range is called the microwave band. And if we use the electromagnetic radiation of this wavelength, and using in the remote sensing purpose, then it is called the microwave remote sensing. Okay, now coming to the wave, because here we should understand the basic things of the interference first, and then we will think how we can monitor the land surface information with the help of the SAR interferometry. So if you see the interferometry, so interferometry is just like the interference of the two or more than two signals. Two signals means SAR signal. SAR signal means microwave signals. Microwave means electromagnetic signals. Okay. So if you see, this is basically the Young's double slit experiment. This is the source of light. It may be, let us say this is the microwave source, and it has, some wave fronts are there, because light propagates in this manner. And this is a particular slit or screen where two holes are there, or two apertures are there. So light will pass from here, as well as it will pass from here. So these sources, or these apertures will act as a secondary sources. So whatever the way of propagation of light from the primary sources, they are the same way the light will propagate from the secondary source also. So you can see that this wavefront is started from the secondary source again in the same manner. Similarly, from this secondary source, the wavefront is propagating in the forward direction in the same manner. So if these two signals, you can see here, both of them, means this wavefront and this wavefront, both of them are intersecting with each other. So at somewhere, they are intersecting, and in between they are not intersecting. So you can say the signals are basically sinusoidal signals. So somewhere they are meeting in the same phase, and somewhere they are meeting in the opposite phase. Opposite means if one signal is having its minima, another signal is having its maxima. If both of them are meeting, it means they are meeting in opposite phase, and this that kind of the interference is called the destructive interference. Here you can see destructive interference. It means this is the first signal, and this is the second signal, and at the intersection here you can see this is the minimum, this is the maximum, and in this manner they are interfering with each other, and then this types of the interference is called the destructive interference, or you can say the opposite interference, or you can say both the signals are meeting with each other in opposite phases. Okay, similarly the other situation might be like this. This is the first signal, this is another signal, and both of them are meeting with each other at the same phase, and this types of the interference is called the constructive interference. So if these two signals are meeting like in this manner, it means a bright fringe will be appear on the screen. Here you can see, and if both the signals are meeting in this situation, then the dark fringe will be received on the screen. Okay, so here you can see this situation, it means both the signals are meeting in opposite phase, and this types of the pattern is there on the screen. So it means this is the dark fringe, and this situation means this situation. So both the signals are meeting in the same phase, it means the bright fringe is received. Okay, so you can say a pattern on the screen will be received where the intensity is varying from maximum to minimum. So maximum intensity means bright fringe, and minimum intensity means dark fringe. Okay, and if you represent this is basically now you can say the fringes or cycle also. For example, bright, then dark, then bright, alternate fringes you will get, dark, bright, dark, bright, dark, bright, and so on. It means alternatively they will form the constructive and destructive interferences. So from dark fringe and bright fringe, both of them is called the one complete cycle. Okay, so if you can represent this complete cycle by different colors also, not necessarily from the black and the white, it may be a color ramp also. For example, here suppose both of them are meeting at the 0 phase or 2 pi phase, and as the phase difference increases, then this is the pink color, then it is pi by 2, then blue color is started, then navy blue at pi, and then again changing another color, yellow at 3 pi by 2, and then slowly red, and here it becomes again 0. So this is the complete color cycle or color wheel, you can say. So the one fringe, or you can say one color cycle, is equivalent. So from here, from dark to bright or bright to dark, we can put a colorful cycle also. So this colorful cycle will help us to monitor the land deformation information or land translation information on the earth surface. So in this way, and this is basically the phase information only, this is not having any amplitude information. Now coming to the SAR interferometry, what is interferometry and how we can find out the deformation on the earth surface with the help of the SAR interferometry. So you see the SAR interferometry or synthetic aperture radar interferometry or InSAR is a tool for measuring the topography. Means this SAR interferometry is not only useful for the deformation, this is also useful for the topography measurement of the earth surface. Topography means especially because the earth surface is having different elevation information also. So if you want to generate the DEM, then DEM you can also generate with the help of the SAR data sets. Okay, and the surface changes you can monitor, and the surface deformation you can monitor with the help of the SAR interferometry. And SAR is a basically complex signal. Whatever the signals we are talking here, these signals are complex in nature because these are electromagnetic signal, and electromagnetic signals are complex in nature. Complex means they have the real part and the imaginary part. Okay, since this is a complex signal, it means it has the amplitude as well as the phase information. So phase information is used for the interferometry, and this from the phase information we can depict the deformation which has occurred on the earth surface. Okay, so the interferometry, at least two signals are required. So let us say the first signal is received from this satellite position of the same area, and another signal is received from this location for the same area. So if both the signals will interfere with each other, then the phase difference between the signals can be calculated very easily, and that phase difference can be converted into path difference, and that path difference means nothing but the displacement of the target, which is moved from one location to another location, or the target is going from downwards to upward or upward to downward. So whatever the motion direction, it is in a vertical direction or the horizontal direction, that path difference can be calculated with the help of the phase difference, and phase difference you can calculate if you have the two SAR signals. Okay, so that's why the two SAR signals are shown here, and these two SAR signals will calculate the phase difference of both the signals. That is called the interferometric phase, and that interferometric phase can be converted into path difference, or path difference is nothing but the displacement or the movement of the targets on the earth surface. So here you can see, this is the mathematical description. For example, this is the earth surface, and this is the typical terrain where the let us say a particular target is at a height of h, and if you want to calculate this h, then first signal is captured from SAR location 1, and let us say from here to here the distance is r, that is the range of the signals, and another signal is captured from this location, and location 2, and the distance is, let us say, r plus delta r, because this distance is not necessarily will be exactly same to this distance, so it is either less than this or more than this, so r plus delta r, or you can say r minus delta r. So this distance is known because SAR signals can easily find out the travel distance from this location to this location, because the speed of the signal is known, and the time of propagation from here to here can be monitored easily. So if you know the velocity or the speed of the signal and the distance, time of the signal, then you can find out the distance or the journey of the signal from one location to another location. So this is known, and at what angle it is the signal is propagated. So this incidence angle is also known, and similarly this incidence angle is known. So if one angle is known and two sides are known, the third side can be calculated very easily. As this separation between two satellites is called the baseline. Means this yellow line is basically showing the direct distance between the two satellite positions. So this is called the baseline, and if you put the perpendicular from one satellite position to the other satellite line, then it is called the perpendicular baseline. So this is a physical separation between the two ecogetions. Okay, so this is also called the spatial baseline, and it is also called the perpendicular spatial perpendicular baseline. Okay, and of course, suppose this acquisition is taken at time t1 and this acquisition is taken at time t2. So there is a time difference between these two acquisitions also. So the time difference like t1 minus t2 or t2 minus t1, this time difference is called the temporal baseline. So these two baselines have a lot of impact on the SAR interferometry. Means if that temporal baseline means time gap between these two acquisition is very large, it means the physical characteristics of this target will change. It means the similarity between the two signals will reduce. If the signals similarity will reduce, it means the correlation will reduce, or you can say the signals will be decorrelated. If, or you can say, in other words, we call it decorrelation effect. So you can say if temporal baseline is very large, then the decorrelation effect will come into the picture and the accuracy of measurement will get reduced. Okay. Similarly, if this perpendicular baseline is very large, it means first acquisition is taken from here, another acquisition is taken from very large distance. It means that location is not completely able to catch this target in a proper way. It means again there is a dissimilarity between these two signals. It means the decorrelation effect will increase. It means if baselines are very large, then the decorrelation effects will come into the picture and the accuracy of measurement will reduce. So our effort in the SAR interferometry will be to keep the spatial baseline or the temporal baseline as minimum as possible. Okay, if these baselines are small, then the measurement accuracy will increase. Okay, and if we take, let us say, 100 images that we are taking and the baselines are very small with each other, Then we can say this is the small baseline analysis, that is called basically SWAS. Okay, so if temporal and the perpendicular baselines are very small, okay, so and those data sets are used in the analysis, then the analysis is called the small baseline subset analysis. Okay, and if these baselines are very large and we are only considering one image as a reference, so from one image if we are considering the reference, and other images may be very large, or spatial baseline is very large, temporal baseline is very large, then this is not called the SWAS. Then we will handle with the help of the PSNSR. Okay, and both the techniques are useful for the time series measurements. Now this slide shows the complete mathematical description of formulation. If you are interested, if you can catch, then just I'm explaining, you can catch. If you are not able to catch, then leave it, because I'm not expecting you are all are from the mathematical background. Mathematical background students can understand it in a better way. If you are not able to catch, leave it. Okay, so this slide explains, like, suppose one target is there on the Earth surface, and initially it is at this location, and after some time this target is displaced to any other position, that is P dash. For example, glaciers are melted, so initially the target was here, then after melting it reached to here. It means some displacement has occurred. Similarly, if our surface, in case of land subsidence, initially the surface was here, and after some times the surface was going downwards and reached at another location, let us say P dash. Similarly, landslide, initially the targets were here, means whatever the land was there, that is initially at this location. After landslide it reached to P dash, it means it is getting displaced. So this displacement, let us say this displacement is D, represented by small d. So now if we are taking the observations from two different satellite positions, A and B. So first observation is, let us say, taken from location A. That time signal is reaching to P and coming back. Okay, so this distance is known, velocity is known, time interval is also known. So phase difference can be calculated. Phase of the signal is also known. Okay, and the amplitude of the signal is known. Everything is known for this signal. And after some time, this point P is displaced to P dash, and that time the acquisition is taken from location B. B means this is another satellite position. So signal is reaching to this target again, but this is another location, because the target is same but location is different. So signal is going to this target, coming back, and each characteristic of the signal is also known. Now we will analyze the characteristics of these two signals. We will try to interfere both of them, and we will calculate the phase difference between these two signals, and that phase difference is just because of this displacement. Okay, so the phase difference is related to the path difference, means phase difference equal to 2 pi upon lambda into path difference. Okay, so this D can be calculated very easily. So here basically I am trying to show any electromagnetic signal is expressed in the form of this E0 e to the power I phi. E0 is the amplitude of the signal, and psi is the phase of the signal. In extended form, we can write E0 e to the power I k dot r minus omega t plus phi, means this is also the phase only, but this is the sum of three terms. One is k dot r, that is called the propagation phase, omega t temporal phase, phi is the scattering phase. Okay, so if we are taking the observation at a particular time, so t is 0, we can say the only the two term will be there, k dot r plus phi, means propagation phase or geometrical phase and the scattering phase. So these two phase we can write for both the signals separately. So this phi a means phase of signal A is the geometrical phase plus scattering phase, means this k dot r plus phi. So this is geometrical phase plus scattering phase. Similarly for the second signal, geometrical phase plus scattering phase. Now it is assumed the signals are propagated at the same time, then the scattering, because the signals are passing through the atmosphere in under the same conditions, so scattering in the atmosphere will be same. So if we calculate the difference between these two, like the phi b minus phi a, so the scattering phase will be cancelled out. And and this can also be achieved like E equal to first signal into complex conjugate of the second signal, because both of them are the complex signals. That's why we are taking as a complex conjugate. So this is the amplitude of the first signal, amplitude of the second signal into e to the power phi b minus phi a. So this is basically automatically coming as a difference of phase of both the signals, phi b minus phi a, phase of second signal minus phase of first signal. So phi b minus phi a is nothing but the interferometric phase, and this phi b minus phi a we can write like delta phi int means interferometric phase. So interferometric phase means phi b minus phi a. So phi b means is a function of time, position. Similarly, phi a is also a function of time and position. So phi b minus phi a we can write phi b geometric minus phi a geometric. Phi scattering is cancelled out because of the similar conditions in the atmosphere. So this delta interferometric phase we can write like this also, because this is the geometrical phase of signal B, this is the geometrical phase of the signal A. So this phase equal to 2 pi upon lambda into path difference. Similarly, here we can write 2 pi upon lambda into path difference. Okay, but in this journey, the path is basically not only one. The path is from here to here, then again here to here. So it means the twice of the one distance. That is 2r. So in place of 2 pi upon lambda, we are writing 4 pi upon lambda. Just the journey is twice. So 4 pi upon lambda is here, 4 pi upon lambda is also here, so that is common. And into path difference for pi second signal, that is bp dash, because from here to here this is the path difference, and minus phi a means first signal, path difference of the first signal, that is from a to p, ap. Okay, so now it is further modified like bp is subtracted and bp is added, and two terms are written here. So this bp dash minus bp, Vp dash minus Bp, this is the deformation phase. Means because if you write another triangle from Vp dash and Bp, so this triangle will be formed. So in this triangle, this side is known, Bp is known, then Pp dash can be calculated. Okay, so this is the deformation, or you can say path difference. Bp dash minus Bp is the path difference, and 4 pi upon lambda Bp minus Ap. Bp minus Ap, so this triangle is formed, and this is the principle of the DM generation using the SAR interferometry, Bp minus Ap. So this can be calculated if you have a very accurate DM. So this phase difference can be calculated. So if this phase difference is subtracted from the interferometric phase, then this path you will get. So, and this path is nothing but the related with the path difference, and path difference is nothing but the displacement of the target from one position to the another position. Okay, so this term is basically this expression we can rewrite like this: delta phi differential interferometry. int means differential interferometry, means the delta phi int minus this term. So here you can say delta phi int minus phi topographic simulation, means this is DM phase. Okay, so this minus this term is called the differential interferometric phase, and which is equivalent to the phi displacement because equal to this term. So you can say if we have the differential interferometric phase, you can calculate the displacement phase very easily. Okay, and this displacement can be calculated as a 4 pi upon lambda into displacement pp dash. Okay, because this is already calculated. Now displacement from p to p dash can be calculated using this particular formula. So this is the basic principle, mathematical formulation of the differential SAR interferometry. Okay, now if we see in the detail, then here you can see the interferometric phase is equal to the displacement phase plus DM phase or the topographic phase. Okay, means this is the interferometric phase only the sum of displacement and the DM phase or topographic phase, but in reality it is more than that. Not only two terms are there, not only this displacement and the topographic phase are there, other phases are also there, like Interferometric phase equal to displacement phase plus topographic phase plus this one. Atmospheric phase is also there because both the signals are passing from the atmosphere, and atmosphere is a very dynamic system. Huge variability is there with respect to location and with respect to time also, because from one position to another position in the atmosphere, the signals will get affected in different manners. Similarly, from one time to another time, the signals are getting affected in different manners. That's why the phase difference between the signal between both the signals is created because of variability in the atmosphere. So in that sense, it is said this interferometric phase is because of displacement, topography, and the atmosphere also. And one is the orbital phase because satellite is continuously moving. So because of the precise orbital positions, because if you don't know the precise position of the transmission of the signal, then you cannot calculate precise phase difference between the signals. Okay. So because of the orbital inaccuracies, some phase difference is also generated because of the orbital motions. Similarly, some noise is there because decorrelation effect or decorrelation noise, we can say, as we discussed, like temporal baseline, spatial baseline. If they are large, and then signal similarity decreases, so decorrelation effect increases. So noise is basically introduced in this. So this interferometric phase is also part of the decorrelation noise plus 2 pi n. This is the n is the number of cycles. It means from the satellite position to the earth surface, we have to calculate how many cycles are there in the propagation of the signals. Okay, so it is not very easy to calculate these number of cycles of the signals during entire journey. Okay, and the phase difference is generated for each cycle. So if phase difference is created in different cycles and it is accumulated and it is exceeding 2 pi, then it is just like one additional cycle is propagated in the signals. But this is not like that. This is because of the phase difference. It means it is the contribution of the individual cycles. It is not the contribution of the separate cycle. So it is very important to calculate how many cycles were propagated from the SAR sensors to their surface during its journey, and that calculation is very, very tough. And if you are able to calculate, then the process is called the unwrapping, phase unwrapping. Okay, so this is basically phase unwrapping term. So in a nutshell, we can say this interferometric phase is the sum of displacement phase, topographic phase, atmospheric phase, orbital phase, decorrelation noise, and phase unwrapping. And also one more term is there, that is called the flat Earth component, because our Earth is not a perfect 2D; it is a 3D environment. So if we convert 3D into 2D, so some phase component is added into it. So we can say that whatever the interferometric phase means phase difference between the signals is the contribution of the displacement, topographic, atmosphere, orbital, noise, phase unwrapping, as well as the flat Earth components of the interferometric phase. Okay, so now here a great challenge started. For example, if you are interested in the surface movement information, it means you are interested in this phase component only. You are not interested in this component or other components. It means other components you have to subtract precisely so that you can calculate this displacement phase precisely, so that you can monitor the deformations or the displacement on the Earth's surface precisely. Okay, so question is how we can subtract these other components. So the subtraction is important. So that subtraction, like flat Earth component I told, so flat Earth component we can subtract by assuming the perfect sphere of the Earth. Okay, so that can be subtracted by assuming statistical models. Topographic phase can be subtracted by using accurate DM. Atmospheric phase can be subtracted. Subtracted means we have to model this component from some other way, and that amount we can subtract from here. It means this is subtracted, and we will calculate the displacement phase accurately. Similarly, orbital phase have to subtract it, and this can be subtracted with the help of the precise orbit files, because each satellite data is providing the precise orbital files. So those orbital files can be used just to remove this phase component. Okay, noise you cannot remove because you have to wear with this, and you know this noise is because of the temporal and the spatial baselines. So whatever the data sets you have taken, it means now further you cannot reduce the spatial baseline, because the spatial baseline is related to the physical position of the satellite. So once it is acquired, you cannot change that physical separation. Similarly, the temporal baseline you cannot reduce, because whatever the time was there for the acquisition, now images you are using, now you cannot change that time. So you cannot do anything with this component, so you have to wear with this, and phase unwrapping can be calculated easily. So this you have to remove, 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 flat earth component you have to remove, just to calculate this phi displacement, because we are interested in the deformation analysis. Okay, so this is the correct way, and the all the components you can remove one by one. All the components you cannot remove at a time. So since we are removing these components one by one, so this is a long process. This is called the interferometric processing chain. Okay, so uh, so the another question here is, if you are interested in land deformation, then you have to calculate this and you have to remove other components. Similarly, if you are creating the DM, then it means you are interested in this component. So in that case, you have to remove this component and these components. You understand? If you are generating the DEM, it means you are interested in this component. You have to remove this and all other components. Okay, so displacement phase means you have to assume there is no displacement, or you have to acquire the data over area where no deformation has happened. It means this component will be automatically subtracted. And sometimes if you are interested in atmospheric modeling, means the signal propagation or signal delays in the atmosphere, it means if you, in that case, you are interested in this component, so in that case you have to remove these components and these components. So atmospheric modeling you can do with the help of the interferometric phase. Okay, similarly orbital files, noise and unwrapping. Okay, so these three applications are major one is the deformation analysis, DEM generation, and atmospheric modeling. Okay, so these three analysis you can do with the help of the SAR interferometry. Please try to understand this, the interferometric phase. Interferometric phase is nothing but the phase difference of the two signals. So phase difference is basically interferometric phase, and that phase difference is useful for the deformation, for the DM generation, for the atmospheric modeling also. Okay, and these components you have to basically whatever you are targeting, the other components you have to remove. Okay, so suppose in deformation case you want to calculate this, so other components you have to remove. So these other components are called the unwanted phase components. Okay, so if your target is here, then these are unwanted phase component. If your target is here, then this and these components are unwanted phase component, and so on. Okay, so this is the detailed description, because this interferometric phase is flat earth. Again, the same slide: displacement phase, topographic phase, atmospheric phase, orbital phase, noise, and 2 pi. So description is flat earth means it's related to the earth curvature, can be easily removed, and displacement phase is the displacement phase related to the coherent movement of the surface. It may be in the line of sight, horizontal or vertical, used to measure land motion from the face. And this is the topographic phase related to the surface height. Atmospheric phase is related to the path delays in the atmosphere due to gas particles, clouds, water vapors, dust, smoke, fog, turbulences, its stratifications, etc. It must be removed for to correctly interpret the InSAR phases. Orbital phase is the related to the orbital inaccuracies, can be removed by precise orbit files. Noise due to decorrelation, temporal, geochronal, and thermal noise, and must live with it. And this is the phase unwrapping terms. Okay, so now whatever the phase difference we are talking, if you plot on the graph in the form of the images, then this look like this. This is the simulated one. For example, this is the similarity. This is a complete color cycle. It is starting from pink and ending on the red. Then again it will start pink to red. Okay, so this is the complete cycle, or you can say this is the one cycle for the wavelength SAR signal with wavelength of 24 centimeter. Okay, and if you see further wavelength it decreased, let us say 5.6 centimeter. So here you can see from red, then pink, and then blue, this up to it is going yellow. So this is one cycle. Then again from red to onwards, this is another cycle. Then again it is started another cycle, and this is another cycle. So this is ultimately 4 cycles are generated, and from red to yellow, it means this is changing, phase is changing by 360 degree from 0 to 2 pi. Okay, so accordingly we can say if phase difference is pi by 2, then path difference will be this much. So path difference can be calculated from the phase difference. Okay, so this is the ideal one, or you can just simulated data, but the practical data will look like this. This is the black and white this is black and white graph of phase difference of two signals. Okay, and in short we call it the interferogram. So interferogram is nothing but a graph of phase difference of two SAR signals. Okay, so this is the black and white, this is the colored one. So this is the color interferogram, black and or gray scale interferogram. So here you can see the cycles are also showing. This is the very standard, but this is the actual one. Here you can see the color is starting from blue, pink, yellow, and then navy blue. Then again it is coming to the blue. So it means the cycle is started from here, ending here, again started, ending, again started and ending. And again you can see here the cycles are very close to each other, means the colors are changing very rapidly over here. It means cycles are very close to here, and here the cycles are very far. Okay, because very far means low movement is there, and the cycles are very close to each other. It means phase is changing very rapidly. It means some disturbance has occurred over this area very rapidly. Okay, so the interpretation here is if the fringes are very close to each other, more disturbance or more deformation is there over that particular place, and fringes are very broad, it means the deformation is low. Okay, so this is the coherence. Coherence is basically similarity, correlation between the signals. So if coherence is low, it means decorrelation is high. You understand? Coherence means similarity is low, it means dissimilarity is high. So we want high similarity. High similarity means high correlation. High correlation means high coherence. So wherever the image has the high coherence, it is much more useful for the interferometric application. If coherence is low, that image is not useful for the interferometric applications. Okay, so if you keep in mind, if coherence is sufficient, means very high, and the coherence values varies from 0 to 1, just like a coefficient of correlation varies from 0 to 1. So 1 means highly correlated, 0 means uncorrelated, you can say. Okay, so highly correlated signals will create or will give the accurate deformation results. Okay, so this coherence can be affected by number of things like baseline decorrelation, temporal decorrelations. Temporal decorrelations may be the wind blown vegetation or some continuous changing of water surface. Precipitations are happening, atmospheric or atmospheric variations are there, then coherence will reduce. Man-made effects are also there, or some phenology is changing, then temporal decorrelation. Because if you are targeting the forest, it means over a period of time, the phenology of the forest is changing. It means the correlation between the signals will reduce. It means coherence will reduce, and coherence is reduced. It means it is not useful in the SAR interferometry, especially. That's why we call SAR interferometry is not much more useful for the natural environment, just like the agriculture targets and the forest targets. It is much more useful in the urban environment or the environment where the sufficient coherence is available. Okay, rotational decorrelation is also there, phase unwrapping is also. This is the formula of the coherence. Coherence is represented by gamma. It is expected value between the two signals, and this one. This is similar to the coefficient of correlation. Now this is sources of errors in SAR SAR interferometry. So one is unwanted phase component, because this is the major source of errors. Because if you are targeting the deformation phase, it means displacement phase, it means other components you have to remove precisely. If you are not able to remove those unwanted phase component precisely, it means your measurements are not correct. Okay. Similarly, the coherence, low coherence makes no sense. Vegetation reduces the coherence. Maybe agriculture, grasslands and forests, natural environments have low coherence. Coherence greater than 0.6 is normally recommended for the InSAR applications. Here you can see, one is high coherence, zero is low coherence. It means everywhere we will not get the 1 or 0. It means if the coherence value is greater than a particular threshold value, then those values can be considered for the interferometric applications. So here it is the recommendation, if coherence is more than 0.6, then we can use for the interferometric application. If it is less than that, then it is not that much useful. Decorrelation effects are there: baseline decorrelation, rotational decorrelation, thermal decorrelation, because SAR sensors, basically electronic devices are there. So with respect to when they are getting operated, they get heated. So because of that heatness or thermal properties, the signal phase difference is changing. So that is also taken into the picture, like the thermal decorrelation or similarity between the signals. Okay, Doppler decorrelation is also there. Processing imperfections like misregistration and uncompensated range migration, phase artifacts. So these are basically some sources of errors in the SAR interferometry processing chain. So if you see the baseline and the correlation, as the baseline is increasing, the correlation is decreasing. So this is the relationship, direct relationship between the baseline, the spatial baseline, and the correlation. Similarly, this is the relationship between the temporal baseline and the correlation. Correlation means coherence. Okay. So as the temporal baseline is increasing, so the coherence is also decreasing. Okay. So this is basically the direct relationship. So you have to keep in mind, if you want to calculate the precise deformation results, you have to take small spatial as well as the small temporal baselines. Yeah, classification of SAR radar interferometry. One is the along track interferometry. It means both the acquisitions are taken in a along track. Means track is same and observations are taken from two different positions. And this types of the data sets you are using, and the interferometry is called the along track interferometry. Across track interferometry means one track is there, another track is any other place, and both the orbits, you can say, or are different, or tracks are different, and these data sets we are using for the interferometry, then the interferometry is called the across track interferometry. Cross track interferometry is also there. Cross track called, suppose you are using some data you are using for ascending paths, some data for descending paths, and these types of the interferometry is called the cross track interferometry. Now, measurement techniques for surface movement. Traditionally, there are a number of techniques like terrestrial methods where people are using the labeling techniques, theoloid, etc. So they are going into the field, collecting the lat long and the relative positions of the target with each other, and they are having an idea, okay, what types of the deformation has occurred. And people are using the high precision GPS technologies also, like GNSS receivers they are putting on the targets for a long period of time, and then they are calculating the precise position of those targets, and those positions, basically Z values or XY values, will tell us in which direction the target is moving. Okay, so that is also one way of calculation of the surface movement of the Earth surface. Another technique may be like the photogrammetry techniques are there, laser scanning is there, differential SAR interferometry, which we are going to discuss, and microgravity methods are also there to monitor the land surface movement. But apart from this differential SAR interferometry, other techniques are very time taken techniques, because the measurements are taken at a point locations only. So if you want to cover a large area, it means you have to take hundreds or 200 observation samples. Okay, so it means it will take a lot of time. It also includes a lot of time, and point data you are basically collecting, you are not able to monitor at each and everywhere. So this is another drawback of these terrestrial or the microgravity methods. So or just to remove these limitations, we are using the differential SAR interferometry because it will give a continuous deformation maps, and the cost, labor cost is also not there, because in other methods we have to move into the field, and survey cost is also there, which is very large. So the survey cost is also not there in case of the differential SAR interferometry. Now, coming to the different types of the differential SAR interferometry techniques. So one is the classical differential SAR interferometry, which we have discussed in the previous slides. So that is the basic technique. Classical InSAR means basic differential SAR interferometry technique, where only two signals are used at a time, and two signals means only one interprogram. One interprogram means from two signals we can calculate the phase difference. So that phase difference we can plot over a single graph, and single graph is called a single interprogram. Okay, so only two images are used, and that phase difference is used in the classical differential interferometry. But question is, if we are using only two images, then we are not able to monitor the deformation over a long period of time, because two images are fixed for two times only. So over a period of time, we are not able to apply the InSAR. But if you want to apply for InSAR, it means we have to analyze these two signals every time. Means from, let us say, from January to December, first, and every month is having one signal. It means we have to first do the InSAR for January, February, then February, March, then March, April, then April, May, June, and so on. So this way we can monitor the time series measurements. Okay, it is basically very time-taking process. So basically we have to repeat the same processing chain for each and every combination of the SAR signals, and then we have to draw the conclusions. Okay, so this is some drawback, or you can say, but basic method is there. And then interprogram is stacking process is also there, because here number of interprograms are generated based on the temporal baselines, and all of them are stacked, and their characteristics are analyzed to analyze the deformations. Another one is the SBAS, small baseline subset analysis. So here again a number of interprograms are used, and each interprogram will have the small baseline. So here basically the master means the reference image is not fixed, means each combination may be like from January to February, February to March, March to April, April to May, and so on. So it means the is perpendicular and the spatial baselines for each combination are very small. Okay, and in other cases the PSI, persistent scatter interferometry, or PSNSAR, this analyze only the coherent point scatters. Here basically the reference image is only one. For example, if images are from January to December, for each month one image is there. So suppose we are taking a reference image of the July month. So the first combination will be from July to January, second combination from July to February, then July to March, July to April, July to May, July to June, then July to August, July to September, July to October, July to November, July to December. It means July is fixed. It means if you are thinking like this, from July to January means temporal time is very large, or you can say temporal baseline is very large. It means decorrelation effect is more in case of PSI, but this large baseline effect is not there in case of SWAS. So in that way we can say SWAS is much more accurate compared to PSI, but both of them can give a very long time series analysis estimations. Okay, this is the PSI component concept. Here you can see number of images are taken. Here on the x-axis we are taking the temporal baseline, and on y-axis perpendicular baseline, and each dot is representing basically the acquisition image. Okay, so this blue dot is considered as a reference image, and we are drawing the line to each and every other point. So this line is basically called the baseline. Okay, so the horizontal side is temporal baseline, and vertical side it is perpendicular baseline. So here you can see from blue to this red, the temporal baseline is small and the perpendicular baseline is also small. Okay, and from this blue to this one, here the perpendicular baseline is large but temporal baseline is small. Okay, and from here to here, if you see, so you can say the temporal baseline is very large but perpendicular baseline is small. So it is basically combination of both. Sometimes temporal baseline and perpendicular baseline both are very large. Okay, but here the reference image is only one. So these combinations are representing one interprogram. From this blue to this red is one interprogram, this blue to this red is another interprogram, and this blue to this red is another interprogram. So here you can analyze how many interprograms you will have to generate. So let us say 100 images are there, so 99 interprograms we can generate in case of the PSI, because reference image is only one. Okay, so what it does basically, these interprograms generate only selected only those pixels in the image where the coherence is more than 0.6 and the phase stability is also constant throughout the acquisition. For example, one pixel you are targeting, so one pixel phase of that pixel is constant in all the images. If any of the image the phase is not that much, or you can say phase is very small, then that pixel will be dropped. So in the entire image only few pixels will be there which are having the high coherence as well as the phase stability, or means the constant phase throughout the acquisitions. So this technique targets only those pixels where the coherence is high or the amplitude is high as well as the phase stability is there. Okay, so those pixels are called the persistent scatterer. So here you can say, suppose this is the pixel, a resolution cell. So within the resolution cell, different targets are there, but one target is there which is giving very high backscatter energy. So this arrow is representing the backscatter energy. So if large backscatter energy is there, it means PS is available in this resolution cell. It means the coherence of this pixel will be high and the phase will be stable, amplitude is of course large, then this pixel will be identified as a PS. And if this type of the situation is there, means no target is there which is giving very high backscatter, but there are targets which are giving a moderate kind of backscattering energy, and those pixels are called the distributed scatterer or the DS. Okay, so in this case you can say that the coherence is moderate, or you can say let us say 0.7, which is slightly more than 0.6. So these types of the pixels can also be considered in the PS analysis. Okay, but these are basically less stable pixels and these are the more stable pixels. Similarly, there may be a two distinct scattering, like this is the one type of the scattering, green arrows and blue arrows are another scattering, and coherence is more than 0.6, phase is almost moderate and stable, then these pixels will also be considered. So all these situations are very specific. Other pixels will not satisfy these conditions, and those pixels will be dropped. Only only pixels which are satisfying these conditions are selected, and this technique is known for selection of such kind of the pixels, and the behavior of these pixels will be analyzed over a period of time with the help of this technique. Okay, and this technique tells us, okay, how the movement is happening from first date to second date to third date to fourth date, and so on. So this is very precise measurements, and these accuracy of these measurements is of few millimeter. Few millimeter means if movement is very slow, that movement you can monitor with the help of the PSI techniques. For example, like tectonic movement, which is very slow, few mm or sub mm in 10 years or 20 years. So that movement can also be depicted with the help of the PSI. Similarly, land subsidence is also very slow movement, few mm per year. So that can be monitored with the help of the PSI. So accuracy is few millimeter. Now this is SVAS. So here you can say on the x-axis is the temporal baseline. This is the perpendicular baseline. Here the master is not fixed or reference image is not fixed, means the combination is marked from, let us say, from one line is from this red to this red. It means this is one interprogram. From this red to this red, this is another interprogram. From this to this, another interprogram, and so on. So basically, for this interprogram, from this red to this red, temporal baseline is small, perpendicular baseline is also small. Similarly, for this in combination. So basically, these combinations are formed in such a way that temporal baseline is small, perpendicular baseline is also small. And again, this technique is also select only the PS and DS. Only these types of the pixels it will select. But only thing is, here we are reducing the temporal and the perpendicular decorrelation effect. Okay, and it basically enhances the accuracy of the measurements further. If you see the the processing chain, so this is the processing chain which we will see in the practical session also. PSI processing chains for the deformation analysis. This is designed for the Sentinel-1 data, which is freely available, and there are different SAR processor like SNAP is there, ISC is there, Gamma is there, SAR Escape is there. So different SAR processors are there. So we have basically done using the SNAP SAR processor. So the pre-processing is done, SAR pre-processing is done in SNAP, and the PSI processing is done in MATLAB using the STAMP PS, Stanford method for PS, means persistent scatter interferometry. So basically, first is SLC images are taken, then split, orbit apply, then master or slab selection means reference and the slab selection, then co-registration, then spectral enhanced diversity, then interprogram was generated, then diverse state, then exported as a PSI, and then in the MATLAB this processing was performed like the candidate weeding, and then phase decorrelation, DM phase was removed, unwrapping was performed, then SCLA atmospheric phase screen was estimated and removed. In this basically we are trying to remove those unwanted phase components, and then deformation and the DM errors were estimated, and that is basically deformation, land surface movement in time series is observed, that finally we can visualize using the R Studio or Stamp PS Visualizer or QGIS or any other GIS software. You can visualize, or you can do some programming in Python or so that you can generate beautiful maps. Now the same PSI processing chain is using for the ISC software. That is, ISC means InSAR Scientific Computing Environment. This is another SAR processor. So the processing chain for this one is like this. Download the orbit files and DM and SLC images, and both were stacked, and an area of interest was defined, workflow parameters are defined, then SLC workflow, splitting, apply orbit file, image co-registration, enhanced diversity, merging, single reference interprograms were generated, then ISC to Stamp PS export. Here Stamp PS export, it means this is Snap to Stamp PS export, and here it is ISC to Stamp PS export, then compatibility file generation for Stamp PS processing, and then same processing was performed for the removal of unwanted phase component, finally visualization of results. And this is the processing chain for the SVAS. More or less up to here it is same, and then single reference stack, then ISC, then SVAS connections were generated. SVAS connections or network formation. This one is basically called the network formation. Okay, so this network was formed, then SVAS interprograms one generated. Here you can see, as compared to PSI, SVAS has more number of interprograms because more combinations are there in the that network. Then rest is the same on removal of the unwanted phase component, and finally visualization. Now this is the coupling of the SAR data for decomposition of the motion vector. Actually, if you are using only the ascending data or descending data, then you are able to calculate only the line of sight deformation only. Okay, and if you are interested in the horizontal and vertical movement also, then you have to couple ascending data as well as the descending data. So for ascending data you should process separately, descending data you should process separately. So from both of them, you will have the line of sight deformation, and those line of sight deformation can be clubbed together, and can be the east based and up and down deformation can be calculated. This is the mathematical formulation. Okay. And this is simple one. Suppose the line of sight deformation is there from one image, let us say ascending pass, and this is the line of sight deformation from the descending pass. So these are basically points which are those pixels which we were discussing. So those pixels are not necessarily you are getting the same by the ascending data sets and the descending data sets. So there may be different. So both of them are basically interpolated over a common grid. So these are discrete values. Now you will get continuous values. Similarly, from this you will get continuous values. And if you have the continuous values, then these equations you can apply, because this equation should be satisfied over each pixel. Okay, so for example, here this pixel is there, but here the pixel value is not there. That's why this resampling is required. So each pixel having the two values, ascending value here, descending value here, both can be used in that equation. And finally, east-west deformation and up and down deformation can be estimated. Recently, we did one landslide study in the Sirmaur district of Himachal Pradesh in India at National Highway 707 near Varwas. So this is the site. So during the landslide, the photographs were taken, which are like this. The entire this land is shifted from this to this deep valley. So the post-disaster, the photographs are like this. This is a very huge landslide over here, and here you can see. So here we use the ascending data sets and the descending data sets also. So using the ascending data set, line of sight deformations were calculated, and those pixels were generated like this, and 3 points were considered just to understand the dynamics of these targets. And same things were done for the descending data set. This is descending one, this is ascending one, wrongly typed here, ascending. Okay. So this again 3 points were considered for detailed, detailed dynamics, and these 3 dynamics were used for the prediction of the landslide. So before landslide data sets were used, and using those data sets, the prediction of landslide was made, and using both the data sets, the vertical and the horizontal data deformations were also calculated. So here you can say for prediction modeling, 2 methods were used. One was the inverse velocity method. Another one was the modified inverse velocity method. This is the completely mathematical model, and this is the graphical model. This is the graph between the inverse velocity and the time. So if you plot this, these lines are for 3 different PS points, like PS1, PS2, PS3. So this is the interpolated plot, and wherever this plot will intersect the x-axis, so that time will basically represent the time of prediction, means time of landslide. Okay, on which date or which day it will happen. So yeah, this is the using the ascending data sets. So those 3, the dynamics of the 3 points, the PS1, PS2, PS3 were considered. Here is the line of sight displacement, this side the observation time. So here is the ancillary information, like first acquisition was considered September 11, 2019, and last acquisition was July 26, 2021. So this is almost 2-year data sets were used, and the actual landslide was occurred on July 30th, 2021, which is according to this one 688th day. It means we have taken the data till July 26, and the landslide was occurred on July 30th, means just after 4 days of the last acquisition. So number of scenes were taken 52, total observation days were this, and we predicted the landslide using inverse velocity method. That was around 690 days, 686 and 685. So actual the event was occurred on 680th day, but our prediction was 690, 686 and 685. Means one prediction was after the actual event, and 2 predictions were before the actual event. So before the actual event prediction means safe predictions. Similarly, the modified inverse velocity method predictions were also done. So this prediction was 690, 688 and 686. So one was exactly coinciding with the actual event. One was after the event. and one was before the event. So the mixed predictions were done using the modified inverse velocity method. Okay. And the same thing, so if you see the time windows, so the inverse velocity method time windows was 6 days, and the modified inverse velocity method time windows was 4 days. So this is the windows for the predictions. Okay. Similarly, the prediction was done for the descending data sets. More or less same results we got, and this way we can basically find out the predictions. So basic understanding of this one is the 0 means the date of the first acquisition, and this 680th day is somewhere here where the landslide was occurred, and the last acquisition was here around 684th day. Okay, so here you can see initially the displacement is 0, and from here onwards the displacement is increasing very rapidly. So from here onwards means after 300 days, means 2 years data sets were taken, means 2 years before the actual event. It means the 300 means just before the 1 year before the actual event, the displacement has started, or it means you can say the instability in the terrain was started just before the 1 year of the actual landslide. And this has occurred because this is across the national highway, and the road widening work was there, so some bombardment was done, and because of that some instability has started in the terrain, and some targets are displaced from original position to another position. Okay, so that is clearly mentioned in these graphs. So displacement has started, and once the displacement has started very rapidly, here you can see. So if the displacement is very fast, it means is the situation of the failure, or you can say landslide. So after that, the landslide was occurred. Okay. So this is from my side. If you have any questions, so floor is open to all. Yeah, any question? Hello. Yeah, any question from the participant side? Are you able to hear me?
Yes, sir, we can hear you.
Yeah, any question?